All right, I guess it's about time to get started. There's no one here yet, but it is 5:30 Thursday afternoon on July 9th, so we're going to go ahead and get started. When we last spoke, we were in chapter 10. We had gotten up through example 10.2, so I'm going to start off with example 10.3. I had already discussed some of the preliminary stuff regarding circular motion. For instance, I showed you the analogs between the kinematic equations and the dynamic equations. Actually, I didn't show as much of that, but I started getting into it. For instance, F equals ma becomes torque equals I alpha. That's a dynamical equation. Or if you want to look at it the new way we learn Newton's second law, which is the net force is equal to dp dt, we can say the net torque is equal to dl dt. That's the two dynamical expressions. But I had discussed, for instance, inertia is the equivalent of mass, and angular momentum is the equivalent of linear momentum and stuff like that. But that's pretty much all I talked about in addition to the kinematic equations. I also showed you that we basically could start from the equation for the arc length on a circle that defines radians that we learned about in trigonometry, specifically the arc length S is equal to R times theta. Your book sort of goes a little bit beyond that and makes the exact parallel, trying to show you that in fact it's not S equals R times theta. They want you to use X equals R times theta or Y equals R times theta or RE or something like that. But that's the main thing is it's that equation. And then if you take the derivative of that, assuming R is a constant, then you get dx over dt or ds over dt or dy over dt, whatever you want to call the left-hand side, s, x, or y. ds over dt, r dx over dt, y over dt is velocity. And then the right-hand side, the r is a constant, so it's going to be velocity is equal to r times d theta dt. But d theta dt is what we call omega, so we have v equals r omega. And then if you take the derivative of that, we get a equals r times d omega dt, and d omega dt is what we call alpha, the angular acceleration or the angular velocity. So the alpha is what we call the angular acceleration, and the omega is what we call the angular velocity, or angular frequency is another one. So those are really all we're going to be using for this first conceptual problem. So we're looking at conceptual example 10.3. And normally with the conceptual examples, I don't necessarily write anything, so I'm not even going to show you the screen, but I'll read it out to you. It says conceptual example 10.3. Is the lion faster than the horse? Sorry about that. Is lion faster than the horse? On a rotating carousel or merry-go-round, one child sits on a horse near the outer edge, and another child sits on a lion halfway out from the center. Which child has the greater linear velocity, and which child, part B, which child has a greater angular velocity? So, in order for you to understand this, I need to explain to you the difference between like a rigid body versus a non-rigid body. So, what we're mainly dealing with in the book in general and in this chapter, especially in the next chapter, especially as well, is we're assuming we're studying rigid objects that basically don't necessarily change their dimensions or sizes in weird ways. So, for instance, if you take, for instance, this Rubik's Cube and you imagine rotating it, you'd say, okay, I'm going to rotate it about here. And you see it does like that. That's a 90-degree rotation. That's a 180-degree rotation. That's a 270-degree rotation. And that's a 360-degree rotation. What you saw is that every part of this rotated through the same angle. So, for instance, when I say a 90-degree rotation, you see that not only did the line connecting the center square right here to the center of the top square, not only did that move by 90 degrees, so did the line connecting the center of the square to the center of this square. So did the line connecting the center of the square to the center of this square. They all moved by 90 degrees. And in fact, if that took a second, then that would mean they moved 90 degrees per second in each case. And that tells us that the angular speeds for a rigid body are in fact the same for every part of the rigid body. Just like the angular displacement, the theta is the same. That's, of course, what we did when I did just the 90 degrees. But once I took the 90 degrees and divided it by the time, then I was comparing the angular velocity. And of course, if I divide that again, if I imagine rotating at 90 degrees in the first second and then let's say 180 degrees in the second, then what you'd find is each of those parts would do it the same way as well. So then you know that not only is the theta the same for each part of a rigid body, but also the omega is the same for each part of a rigid body. And then finally, that last thing showed us that the alpha, the angular acceleration, is the same for a rigid body, for all parts of a rigid body. Now, if you want to think about something that's not a rigid body, let's take, for instance, this eyeglass cleaning case, cloth, excuse me. If I start to rotate that, you can see I'll sort of pinch it in the middle so you can see what's going on here. In principle, I can turn like this, and you see that now it's actually not as easy to see as I'd hoped because it's vertical instead of horizontal. But what you see when you rotate such a thing is you can actually rotate the middle like 180 degrees, and the parts on the outside might not rotate at all. For instance, we can do it like this. If I rotate this way, that part right there hasn't moved at all. So that's the difference between a rigid body and a non-rigid body. When you're talking about a non-rigid body, then yeah, angular acceleration, angular velocity, and angular displacement change from point to point to point. But in general, when you have a rigid body, they don't do that. So that's key to understanding this conceptual example three. It says on a rotating carousel on our merry-go-round, one child sits on a horse near the outer edge, another child sits on a lion halfway out from the center. Which child has a greater linear velocity? Well, remember, we started with s equals r times theta and took the derivative, and that gave us v equals r times omega, and the v is the linear velocity. What we see is the v is equal to the distance you are away from the center because v equals r omega. So it's v equals r, the distance away from the center, times omega, the angular velocity. But the omega is the same for both the lion on the outside edge or excuse me, the horse on the outside edge and the lion halfway out. So you can see that the velocity for the horse that's all the way out near the edge is twice as big as the velocity, the linear velocity for the lion that's only halfway out. So that gives you part A, which says which has the greater linear velocity. The one that's farthest away, since v equals r omega, and omega is the same for both, the one with the largest r gives us the largest v, and that means the horse goes the farthest, and therefore the horse has the greater linear velocity. In part B, it wants to know which child has the greater angular velocity. In that case, they're exactly the same because, as we said, this is a merry-go-round. It's a rigid body. We don't expect, for instance, if this is the center of the merry-go-round right here, and then the horse is, or excuse me, the lion's here and the horse is here. If I turn 90, they're still in that same line. So this lion went 90 degrees, this horse went 90 degrees, and so on and so forth. So that's why the angular velocities are the same for all of them. Anybody have any questions on that? All right, well, let's get to example 10.4. And for this one, I'm going ahead and sharing my iPad screen. Oops, I hit the react button, and that's different. Nobody was here when I got here, so I feel obligated to still go ahead and ask you guys, does anybody have any questions before we get started more deeply? I know we've covered one example already, but we certainly can take a question if you have any. Okay, I've got the chat window opened again now. It looks like most people have went ahead and chatted me your first and last name, as you should. And it looks like no one's typing any questions, so I assume that means we can move along. So we're going to move along to example 10.4, and example 10.4 says angular and linear velocities and accelerations. A carousel is initially at rest. At t equals 0, it is given a constant angular acceleration alpha equals 0.060 radians per second, which increases its angular velocity for 8.0 seconds. At t equals 8.0 seconds, determine the magnitude of the following quantities. A, angular velocity of the carousel. B, linear velocity of a child located 5.5 meters from the center, point P, in figure 10.8b. C, the tangential linear acceleration of the child, D, the centripetal acceleration of the child, and E, the total linear acceleration of the child. So that's what we're trying to do. Let me write down what we know now. So we're looking at example 10.4. And what information we're given is V0 equals omega 0 equals 0, and that all means that t equals 0, and alpha is equal to 0.060 radians per second. Radians per second squared is the easier way of writing it. But again, I want you to think in terms of radians per second, because that means that its angular velocity omega is going to change by 0.060 radians per second each second. So after 1 second, its angular velocity will be 0.060 radians per second. After 2 seconds, it'll be 0.120 radians per second. After 3 seconds, it'll be 0.180 radians per second. So that's why we tell you that. We are asked specifically for at t equals 8.0 seconds. We want to know the angular velocity, so omega equals question mark, and I'll write CA for carousel. And B, we want to know the linear velocity of the child. So this is V tangential is what we're talking about here. When I write S equals R times theta or X equals R times theta and then take the derivative, I get V equals R times theta. That V is called the tangential, and also sometimes they're reported as the linear velocity as well. So a V tan equals R times omega, or V linear equals R times omega. Similarly, once you take the derivative of V equals R times omega, you get A tangential equals R times alpha. Again, that's A tangent or A linear as well. So in this case, they're asking for the linear velocity of the child. So I'll say CH instead of CA equals question mark. And the child is at 5.5 meters from the center. So I'll say at R equals 5.5 meters. And then part C, they want to know the tangential linear acceleration of the child. So A tan child equals question mark. And then part D, they want to know the centripetal acceleration of the child. So we're going to call that radial r centripetal. I don't want to use a subscript C for obvious reasons. I've got a child there. So I'm going to say A sub R, and then I'll put a CH on that. And then finally, for part E, they want to know the total linear acceleration, and I'll explain that as well. So they want A total for the child equals question mark. Solution. Well, we're going to have to figure out the angular velocity given an angular acceleration. We know, for instance, if we had an initial velocity of 0 meters per second and an acceleration A of 0.060 meters per second, and we were asked what the final velocity would be after 8 seconds, then we'd know we could use V equals V0 plus AT. So by the same reasoning and the analogy that I showed you before, that means we should be able to use omega is equal to omega 0 plus alpha t. That's the rotational analog to V equals V0 plus AT. So that's one of the equations we're going to use. Another equation we're going to use is V tan equals R times omega, and A tangent is equal to R times alpha. And we can also use that A radial is either V squared over R, but we also know V is equal to R omega. So we could say R omega quantity in parentheses squared over R, which gives us R times omega squared. So that's another equation we could possibly use, and we'll probably be using that quite a bit. So let's go ahead on with part A. Part A, they want to know the angular velocity of the carousel at 8.0 seconds. And of course, every part of the carousel and everything rigidly attached to it or even anything just sitting on it but not moving is going to have the same angular velocity. So I don't have to specify child or carousel or anything like that. I'm going to say omega is equal to omega 0 plus alpha t, which is equal to 0 radians per second plus 0.060 radians per second times 8.0 seconds. And of course, 8 times 0.06 would be 0.48. So this is 0.480 radians per second is equal to omega at 8.0 seconds. And we're assuming that pretty much it's going to accelerate at that constant acceleration up until 8 seconds. And then either it's going to continue accelerating at that same rate or the acceleration is going to go to zero and it'll constantly spin. Luckily, they don't ask us any of those questions. So all we have to know is that it did a constant acceleration up to the 8 seconds. So now for part B, we want to know V tangent. So V tangent, oops, left off a critical letter here. V tangent is equal to r omega. And of course, that omega, like I said, is not just the carousel, it's for every part, including the boy. So in this case, we're going to say the distance that the boy is away is the r, and that is 5.5 meters. And we're going to multiply that by the angular velocity, which we just discovered was 0.480 radians per second. And in this case, we could multiply, well, actually, rather than try to use my head to work this out and make a careless mistake, I'm going to go ahead and use my calculator. 5.5 times 0.48 gives us 2.64. And that's one extra digit beyond the sig fig, so that's 2.64 meters per second equals V tangent child at 8.0 seconds, which is what they asked for. Now for part C, they want to know the tangential linear acceleration of the child. So for part C, oops, so writing in red. For part C, what we're going to use is we want the tangential linear acceleration, and that is given by A tangent is equal to R times alpha. We know what alpha is. It's the 0.060 radians per second. So all we have to do is go about figuring out what that will be once we know that the child, of course, is out at a distance of 5.5 meters, because in part C, they're asking for the tangential linear acceleration of that child. So with that in mind, all I'm going to do is take A tan equals R times alpha. The R is 5.5 meters. The alpha, as best we can tell, is 0.060 radians per second. So from that, you see we're going to get meters per second for the units, and 5.5 times 0.060 gives me 0.33. Carrying one extra digit beyond the sig figs gives 0.330, and that's meters per second is equal to A tangent child at 8.0 seconds. Again, I'm just writing all that for clarity so you'll know that we were actually doing it at that particular time. But that's part C. Part D, they wanted the radial acceleration. So in this case, we're going to say D, and what we know is A radial is equal to V squared over R, but we also found out that that could be written as R omega squared, because V is R omega, and when you square that, that'd be R squared omega squared over R. One of the R's cancel out, and we just get R omega squared. And that is the better thing for us to use here. So I'm going to use that. I'm going to say 5.5 meters for the R, and then the omega squared is 0.060 radians per second squared. So in this case, wait a second. Oh, sorry about that. I almost used the alpha instead of the omega. That would have been really bad, but luckily I caught myself beforehand. So I did say it's omega, not alpha. So anyways, we're going to go ahead and use the omega, and we did find the omega was in fact, oops, I circled the wrong part. Let me fix that real quick. I circled the descriptor part, but not the actual answer part, which was the whole purpose. Anyways, there is the actual answer part. I'm going to pull back here and say like that. So really the omega that we're wanting to use is the 0.48. So I'm going to say 0.48 radians per second. And the reason that I figured out I had put the wrong thing in is I was looking at the units and I was getting meters times radians per second squared, and that would give me radians per second per second per second per second, which is not what we're shooting for at all. So now all I have to do is take the 5.5 and multiply it by 0.48 and then square the 0.48. And when I do that, I get 1.267. And of course, that's only supposed to have two sig figs. Excuse me, sorry about that. So I'll underline the 6 and the 7, and you see that the units work out to meters per second, and that of course is A sub r for the child at 8.0 seconds. So I'll box all that off. And now all we have is part E, and that means finding a total. So E, and this is the part I have to explain to you. If you read the chapter, you know what it is already, but basically we have two components of acceleration. We're going to have the component of acceleration that's tangential to the velocity. In other words, it's parallel to the velocity. And then we have the component that points radially inward or outward. So we have a radial component and a tangential component. So A total as a vector is equal to A tangential plus A radial. And then, of course, those are automatically perpendicular directions. So if you want to actually find the vector quantity, then you're going to add them like vectors. And when you add them like vectors, they're at 90 degrees. So you're just doing the Pythagorean theorem. So we begin as follows. We know what A tan is. We know what AR is. And in fact, if we drew the arc of the motion that, say, the child is going through, we might say that the child is going through some kind of arc like this, and I don't know where that line just came from, but that was kind of weird. Anyways, we're going to say the child is roughly here, and the child is actually accelerating as a result of a tangent this way, and the child is accelerating inward as a result of a sub r like that. And we know what those quantities are. Specifically, we know a tangent is equal to 1.267 meters per second. And we know that AR, oops, that was the opposite one. Sorry about that. I took the radial one for the tangent one. So this is 1.267 meters per second, and the A tangent we found was 0.33. And that's meters per second like that. So the A total magnitude, and actually I can start writing in blue again now. The A total magnitude, I can try to write in blue. So A total in magnitude is equal to the square root of 0.330 meters per second squared plus 1.267 meters per second squared, quantity squared, square root of all that, Now, this is where you get a little crazy with the sig figs because you have to actually check what 0.33 is because you only have two sig figs and you got to see where, since you're getting ready to add, you got to see where the last decimal place is that's actually a significant figure. So when I take 0.33 and I square it, I get 0.1089, but I only had two sig figs, so that means it's only good to two decimal places because 0.1089 it doesn't have a whole number part, so it's just the one and the zero, which would be 0.11. Similarly, when I do 1.267 squared, that also had only two sig figs, and that turns out to only have, it's supposed to be 1.605289, but it only has two sig figs. That means the 1 and the point 0.6, the 1 and the 6 are the sig figs. That means it's only good to one decimal place. So I've got to add the 1.605 plus the 0.1089, and that gives me the square root of 1.714, like that roughly, and that's meters squared per second to the fourth. And what we just discovered was the only sig fig is the whole number and the first decimal place. So we now still have only two sig figs. Now I'm going to take the square root of that by raising it to the 0.5 power, and that gives me 1.31 with one extra digit, of course, 1.31 meters per second is equal to A total. So I can circle that off. That's the magnitude. But remember, A total is technically a vector quantity. So we need to know roughly something about its magnitude. Now, what we know is this guy, the horizontal one or the tangential one, is only 0.330 meters per second. And then the other one is about almost three times, actually, definitely almost four times as long. So we're going to say it's roughly like this. And that's actually still a little bit short, but somewhere around there, that's going to be 1.267 meters per second. So that's what our actual two vectors that are added together are giving us, and therefore we can figure out what this angle right here is phi by saying tangent phi is equal to opposite over adjacent. So that'd be 1.267. I'll leave the units off over 0.330. Therefore, phi is equal to the tangent inverse of 1.267 divided by 0.330, which should only give us two sig figs. So if I just say shift tangent inverse, shift tangent inverse, parenthesis 1.267 divided by 0.33, that gives me 75.4 degrees. As shown, I'll just say as shown. So in other words, by saying as shown, I'm telling you, look at my diagram, that explains what that angle phi is. Anybody have any questions on that? Your book actually gets an answer of 15 degrees, which you'll notice is pretty much the complement to this. So they ended up doing the opposite angle that I did. They would have done, for instance, this angle right here, which you might call theta, and then you'd say theta is about 15 degrees. So, uh, any questions on that? All right, some other information that you need to know because we're going to use this not only in this chapter and the next, but also when we get to chapters 14 and 15, which is where we go after chapter 11. So I want to teach you some general stuff about motion. I've given you a little bit of this already when we first started about Hooke's law, but I just want to point out to you again. With rotational motion, you not only have this angular acceleration or this angular frequency, you have an angular speed, and we're used to the thought of angular speed in this chapter because that's what we're talking about. But it also has to be interpreted, the omega, as an angular frequency. And in that case, we're talking about circular motion. And when we say frequency, we talk about the number of cycles. There's one cycle, two cycles, three cycles, the number of cycles per second. So frequency F, oops, sorry, it's on that write better stuff. So F is what we call frequency, and it's equal to the number of cycles divided by the number of seconds. So if you watch a cycle, you watch something repeat itself, which could be circular motion, or it could be, for instance, spring motion, where you go from the equilibrium point of the spring to the max extension, back through the equilibrium through the max compression, and then back to the equilibrium. That's one cycle. Okay, so that's another way of looking at it, because it then repeats itself again. There's another cycle, so on and so forth. Or you could be talking about a circle, one cycle, two cycles, three cycles. If you count the number of cycles and then divide by the number of seconds, you get the frequency. And in fact, that frequency is measured in units of, they either call it CPS, which you'll see in some old government documents, for instance, but it's also in units of hertz. And the hertz is abbreviated capital H, lowercase z. So, for instance, the electricity that we use in our houses is a 60 hertz AC signal. So, the frequency of that radiation, or excuse me, the frequency of that voltage change is in fact 60 hertz. So that gives you some idea. There's also omega, which is the angular frequency. We already talked about it being the angular velocity, and it is that too, but it's also called the angular frequency. And that is, in fact, just taking the frequency that we just talked about and converting it from hertz to radians per second. Or you could, of course, say cycles per second is sort of relevant as well, but the main thing is we generally use frequency, or we usually use it as radians per second. And the formula for that, of course, is 2 pi radians per cycle times the frequency f. So that's a very important equation. Omega is equal to 2 pi times f is an equation that we need to know. And just like frequency is cycles per second, that's another expression we need to know. And then there's also another thing that we talk about when we talk about repetitive motion, stuff that goes in a cycle or some repeating pattern or whatever. So that other thing that we talk about is the period. So I'm going to write right here, T equals the period. And that could be the period of oscillation, the period uh, revolution, stuff like that. But the main thing is that period is measured in seconds. It's a unit of time. And you might imagine, for instance, if someone says the frequency is 2 cycles per second, then you'd say, well, how many seconds does it take to complete one cycle? Since 2 cycles are completed in 1 second, then one cycle must be completed in a half a second. And you see that the frequency, since it was 2 cycles per second, is 2. And it's no coincidence that the period is 1 over 2 or zero point 0.5. In fact, that's another fundamental equation. The frequency is equal to the 1 over the period, or the period is equal to 1 over the frequency. So both of those are equations that we'll use from time to time as well. And you can see that you can combine them so that you get omega is equal to 2 pi over the period as well. That's going to come in handy because later we're going to talk about a wave number, and a wave number is k is equal to 2 pi over lambda. So that's something else that's coming. But we'll talk about that later when we get there. Anybody have any questions on that description of stuff? I saw Mihak came in. Mihak, feel free to go ahead and type your first and last name into the chat if you want to. We're moving on to the next section, and this is where they talk about the vector nature of angular quantities. And what I want to tell you is if you're imagining, for instance, rotating this Rubik's Cube like this, then there's a couple different ways. If you want to express it as a vector, you might have to consider a bunch of different things. Like you might say, okay, I'm rotating it this way. And you might say, okay, I'll represent it by a vector pointing that way. But you can't make a good argument as to why you're pointing it this way instead of that way. But not only that, you can't even make a good argument for why you're pointing it that way, not this way, not this way, not this way, not this way. There's literally an infinity of ways you could allow a vector to point that happens to be consistent with the rotation. So in terms of thinking about a vector quantity for a rotation like this and saying it's going to be one of these directions, there's no good reason for it to be any of those directions. So we're not going to use any of those directions. What is fairly less redundant or less complicated is what if I choose the direction parallel to the axis of rotation? Then you only have two quantities. You could say it's rotating this way and you could call it this vector, or you could say it's rotating this way and call it this vector. So we had two choices, and what we chose to do was make it unambiguous by convention. And the convention is we're going to use a right hand rule. So the right hand rule can be applied by this: if you lay your hand in such a way that it's like you're holding a straw in your fingers here, or like you're holding this pencil in your fingers here, if you hold a pencil like that parallel to the axis of rotation, if your fingers happen to be curling around in the same direction that the object is rotating, then and you're using your right hand, then the right thumb points in the direction. So that's the actual direction of these angular quantities. So let me just show you really quickly on this. If we, for instance, had a disk, ooh, that's the wrong one. If, for instance, we had a disk like this and it was rotating this way, then our right hand rule would tell us omega would point that way. Okay. Similarly, if you had a disk that was rotating, actually, I want to go the other way. If I had a disk rotating that way, now I've got to take my fingers and curl around that way so that they match, in which case my angular velocity would be that direction. So that's the convention that we've decided upon for these vectors that represent angular quantities. So if theta is rotating like this, then the direction for theta is that way. If the velocity is rotating like this, then the omega is that way. And same thing with alpha and so on and so forth. And you can talk about, for instance, if it's slowing down, it might have the opposite direction, so on and so forth. But they'll talk about that in section 10 too. I just wanted you to know that's what we do. The problem is these vectors are called axial or pseudo vectors. These, oops. These are axial are, oops, pseudo, P-S-E-U-D-O vectors. So they're either called axial vectors or pseudo vectors. And the main thing is a pseudo vector and that is actually one word, so I should put that inside one set of quotation marks. But pseudo vector, those are vectors that aren't strictly speaking vectors, and that doesn't come into play unless you go further on and become a particle physicist or someone who works in the fields of like group theory and stuff like that. That's a little bit problematic. Just know that these particular vectors are not strictly speaking vector quantities. They don't obey the laws of vector mechanics like we expect them to, or the laws of vector algebra that we expect them to. So just keep that in sort of the back of your head, probably unless you're majoring in physics or mathematics. you're probably not going to run into it. If you do, however, go into the upper echelons, and I say upper, not necessarily to say that it's in some sense better, but if you go to the higher levels of degrees in engineering, you might actually run into the branches of mathematics in which that's relevant too. So just keep it there. The way you can tell that they're pseudovectors is this, though. Your book does this description. So, for instance, if you take this water bottle and you say, okay, let's put it in front of a mirror, and when it rotates this way, the right-hand rule tells me that the vector's that way. Now, if I'm looking at that mirror image is showing it when I do this, it's showing the side closest to the mirror going down. Well, in the mirror image, the side closest to the mirror going down is this side over here, not that side. So it's actually rotating the opposite direction in the mirror. And therefore, the right hand rule gives you a vector pointing this way in the mirror, but this way outside of the mirror. And mirror images are supposed to be exactly the same for vectors. So that's what makes them a pseudovector. So that kills section 10.2, which is on vectors, axial vectors, pseudovectors, and why they're different. The constant acceleration part, we've already talked about those equations. I just gave you those and even explained how to get them, even though I didn't feel there was any need to derive them because we did all that in chapter 2 with the regular kinematics. It's just different symbols, but the same process. So let's jump into example 10.6. Draw this line here. I'm going to say example. Dang it, I just changed it from that. Okay. Example 10.6 says centrifuge acceleration. A centrifuge rotor is accelerated for 30 seconds from rest to 20,000 RPM, which is revolutions per minute. A, what is the average angular acceleration in radians per second per second? And B, through how many revolutions has the centrifuge rotor turned during its acceleration period, assuming constant angular acceleration? So, what we're going to say here is omega 0 is equal to 0 because it said a centrifuge rotor is accelerated for 30 seconds from rest. The from rest is why I reached the conclusion that omega 0 is 0. And it said to 20,000 RPMs. And RPMs could go sort of either way with the F or the omega. I'm going to go ahead and call it the omega. So I'll say omega final is equal to 20. Oops, put my comma too early. Is equal to 20,000. And this time it's revolutions per minute. But if I really want it to be a omega, I need to convert that to radians per second. So I'll go ahead and do that. And you don't always have to. It's somewhat about what the final problem is. But I'm going to go ahead and write that down. So I'm going to first off convert this. One revolution is equal to 2 pi radians. And then I'm going to say that 1 minute is equal to 60 seconds. So you can see now that the minute cancels out with the minute and the revolution cancels out with the revolution, and it gives us radians per second. So I'm going to take the 20,000, 20,000 times 2 times 3.14159, and then I'm going to divide all that by 60, and that's going to give me 2,094. Which we really only had at best, well, we definitely have one sig fig, but I'm going to go on the assumption, since they gave us 30 seconds, I'm going to go on the assumption that they gave us two sig figs. So I'll say 2094 radians per second is the angular velocity. And they said they did that in delta t equals 30 seconds. And by me writing 0 point and then a 0 with an underbar, that's telling you that I'm assuming the 3 and the 0 are in fact sig figs, but the second 0 is not. So well, they want to know what is the average angular acceleration. So A, they want to know alpha bar is equal to question mark. And then part B, they want to know through how many revolutions. So theta in revolutions is equal to question mark. So this is one of those scenarios where they say, where I was telling you, you might not want to necessarily convert the omega from radians to revolutions or from revolutions to radians. In this case, we're actually asking for an answer to come out in radian or to come out in revolutions. So it might be better. It's just a matter of looking at the equations and making sure that that's kosher. So let's go ahead and solve this problem. Solution. Oops. This thing automatically just flips to that make my drawings better scenario all the time, and it's aggravating to me. It's one of the reasons I don't like this app that I'm using too much. But the solution is going to require us to say alpha bar, we learned this before, was omega final minus omega 0 over delta t. So that could easily come out in times of, or in units of radians per second per second. I'm going to just stick with that because we did do it already. So I'm going to write 2094 radians per second minus 0 radians per second. And then all of that divided by 30.0 seconds. So we get 2094 divided by 30. And that gives me 69.81 radians per second is the average acceleration. Now, if we assume the acceleration is a constant, then the average acceleration is the acceleration, and that's the key thing to understand. So now we have that. There's A. So part B, they said through how many revolutions has the centrifuge rotor turned during its acceleration? Well, we can use an equation. For instance, if we were given the omega final and the omega initial and the delta t, that gave us a way to calculate A, or alpha. Similarly, if we had V final and V initial and time, we could calculate A average. And then if they told us that A average was a constant, or that we could assume it was a constant, then any of our kinematic equations for constant acceleration would work. So for instance, we could use V squared equals V0 squared plus 2A parentheses, X minus X0. But that would allow us to solve for X minus X0. In this case, the rotational analog is omega squared equals omega 0 squared plus 2 alpha times theta minus theta 0. We could use that, but we could also use 1/2 AT squared plus V0t plus X0 is equal to X. The rotational analog being theta equals 1/2 alpha t squared plus omega 0t plus theta 0. Sorry, I had something in my throat. It still bothers me. So I'm going to use that other equation. Let's say theta equals 1/2 alpha t squared plus omega 0t plus theta 0. We're going to assume that theta 0 is 0 because we're just wanting to figure out how many turns it made during the acceleration time. But we also know that it started from rest. So we can say that omega 0 is going to be 0. We do happen to know the time and we do happen to know the acceleration. So now I can go ahead and write theta is equal to 1/2 69.81 radians per second times 30.0 seconds quantity squared. And this is going to be 0.5 times 69.81 times 30 squared. And that's going to give me 31,415. And that is radians. You might notice that looks a lot like pi. Pi is 3.14159. So this is like pi times what? 10 to the fourth. So we could say pi times 10 to the fourth radians is approximately what it is. But in all honesty, we only had 2 sig figs, so the 415 is not relevant. But still, to 2 sig figs, we can use pi times 10 to the fourth. And with that in mind, that actually allows us to figure out the number of revolutions, because specifically they're saying through how many revolutions. We know that 2 pi is 1 revolution, so if we divided this by half, we get the number of revolutions. Or alternatively, you could just do it like this. I'm going to say pi times 10 to the fourth radians. I'm going to put that over 1, and then I'm going to say pi radians is equal to, well, actually, let's go ahead and do 2 pi radians. 2 pi radians is equal to 1 revolution. So if I say pi times 10 to the fourth and then divide it by 2 pi, then I get 1/2 times 10 to the fourth, and that's revolutions. Well, 10 to the fourth is 10,000, and half of that would be 5,000. So we're estimating that this should be roughly 5,000 revolutions that transpired during that 30-second interval. Anybody have any questions on that? And that's the same answer they got. As I said, you could have also used omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. If you did that, of course, the theta 0 would be 0, the omega 0 would be 0, and then we just get from that, that theta would be equal to omega squared over 2 alpha. That's going to be 69.81 radians per second squared over 2 times, oops, I actually put the omega in the wrong spot. But here's something neat, because we did do this, I can go ahead and show you that this equation might actually work out with the original formula. We know the final angular speed was 20,000 revolutions per minute. So the only problem would be is the unit of minutes. So 20,000, we could write 20,000 revolutions per minute. And if I made that revolutions per second, then it would work fine with the acceleration that's downstairs. So I'm going to go ahead and say 1 minute is 60 seconds, like that. And now I'm going to square that quantity and divide it by 2 times 69. In this case, I don't necessarily want the alpha to be in radians. I want it to be back in revolutions per second. And to do that, that would require me to use the 20,000 times the 20,000 divided by 60. 20,000 divided by 60 would be 333, and that would give me revolutions per second per second. So to do that, I can go ahead and call it 333 revolutions per second. And this time it should come out straight out as 5,000. So let's check it out, see what happens. I'm going to say 20,000 divided by 60. We just did that and got 333.3333. Now I got to square that, and then I'm going to divide that quantity by parentheses 2 times 333.33. And this time it gives me, did I remember to square everything? Yes. Oh, stupid me. I forgot to divide the 3333 by 30 because that's what the alpha has to be. So the 3333 was just the top part. It was the revolutions per second. But we want the revolutions per second per second. So I have to actually go ahead and divide that by the 30 seconds. So 333.33 divided by 30 is going to give me 11.11. So that's what I really have to divide by. Hopefully this will work out. Anyways, let's check it out. So I'm taking 20,000 divided by 60. That gives me the 333.33. I'm squaring that, And then I'm dividing that by parentheses 2 times 11.11, which is extra sig figs. And sure enough, I get 5,000 revolutions. So you see, you can actually have done this with the revolutions units, but it'd be a little bit more complicated. For instance, I just did all that sort of in my head and explaining it to you to get the 11.11, but hopefully y'all can go back now and figure out how I did that, or hopefully I explained it well enough that you understood it then. But definitely when you're reading it, you want to try to do that as well. And that's really what you're supposed to be doing when you're reading your textbook as you go along. You should be working these examples on your own, ideally working them before you even see them solve it. But if you can't do that, then that's perfectly normal. It's nothing wrong with you. But they're hoping that they taught you enough at that point that you could actually solve the example yourself without their assistance. So give yourself that try by, sort of covering up the solution and seeing if you can work it out really quickly, or at least thinking through the solution, what equation am I going to use, that sort of thing, and then look at the example and see if that worked out right. If it did, then, pat yourself on the back for figuring it out. If it worked out wrong, you still might not, or if it worked out differently, you still might not have done it wrong. You might just be doing it a different way. So if that comes up, you want to go ahead and plot on through and see if you can get the answer. And if the answer comes out to the same answer, then you're probably, with very few exceptions, you're probably did it an acceptable way. Okay, so do that. The same thing with the little exercises. Sometimes at the end of a example, it'll have a little exercise where you're supposed to do something. You're definitely supposed to be doing those as well as you go. So, the Holy Grail, of course, once you finish reading a chapter and before you start doing your homework and before you start doing practice tests, the Holy Grail would be, can you open the book to each example in that chapter and without looking at the solutions, read the problem and then solve it yourself? If you can, then you can be pretty confident that you're in a pretty good spot to begin your homeworks as well as to begin your practice tests. Any questions on example 10.6 before I move along? All right, now we're going to talk about torque. And torque here, we normally cover it in the second chapter, in the chapter 11, where I give you the more formal formula, but I go ahead and do everything right up front. So I'm going to go ahead and mark off the end of this example with a well-drawn purple straight line. And now I'm going to turn that well-drawn app part out so that it won't do that to my handwriting or anything. But I want to make an argument to you about how easy it is, for instance, to loosen a nut with a wrench. So let's imagine, for instance, you have a typical hex nut like this. Now, a hex nut has, of course, 6 sides, and this would be the threaded part, the circle there in the middle. And what I want you to think about is a wrench. So here's a wrench, and it happens to be exactly the right size wrench, so it fits quite well. And now I want you to think about the various things that you could do to make this, oops, might should have kept those straight lines up there a little longer. Now I want you to think about what you can do with this wrench to make you have a better chance at loosening it, for instance. So I'm going to take the wrench and imagine it's got a really long handle, and you'll see why that's the case in a second. So we'll say that's basically the wrench. Now it is lefty loosey, righty tighty in general, so we're going to assume that this is loosening. When they say lefty loosey, righty tighty, what they mean is look at the thing and look at the top, and if the top goes to the left, that's loosening. If the top goes to the right, that's tightening. Now, I want to think about the things that could matter in our ability to turn this nut off. So this nut could be so old and corroded to it that it's really, really hard to get loose. And this is a very common thing when you're working, for instance, on cars and boats and trucks and stuff like that, or lawn equipment or farm equipment, that sort of thing. So first off, I want you to think about, would it be just as effective to put my hand right here, or would it be more effective to put my hand over here to try to loosen it? Which one? A, or B, which one would be better at making sure I can loosen this nut? Would it be pulling up on the wrench at A or pulling up on the wrench at B? Anyone? There's a great quote from Tom Hanks' character in Apollo 13. He said, "What did the guy say? Give me a lever large enough and I can move the world," something like that. That's sort of what we're thinking here, okay? We need specifically this quantity is called the lever arm. When you go to rotate something, you apply a torque to it. Torque causes rotation. It also causes what we call angular acceleration. Whereas we've been using F equals ma for linear acceleration, there is an exact analog to that, which is torque. The sum of all the torques acting on the system is equal to I times alpha instead of M times A. I being the moment of inertia we talked about last time, and alpha being the angular acceleration. So the rotational analog to force is torque, and the rotational analog to acceleration is angular acceleration. And what I'm telling you is this torque quantity depends on what we call the lever arm. And the lever arm is the distance from the center of rotation to the point of application of the force. So let me write that down real quick. Lever arm is the distance from the center of rotation to the point of application of the force. So hopefully you now see that when I ask you, will pulling up at this point A or pulling up at this point B allow me better chance of rotating this nut? And no one answered, but you can see hopefully from that that at point A, the lever arm is just from here to here. And at point B, the lever arm is from here to here, and that's a much longer lever arm. And what you were supposed to answer was that if you really, really wanted to loosen this nut and you were having a hard time, then you want to definitely put your hand as far away from the center as possible. Because of that, we reached the conclusion that okay, torque is directly related to R, and R is what we call the lever arm. And I'll say approximately R because really we picture it as a vector that points from the center of rotation to the point of application of the force. So I'm saying the distance, the magnitude is sort of the lever arm when in fact it's the whole vector. But anyways, we do see that because putting my hand at A produced a smaller lever arm than putting my hand at B, we do see that B was more likely to give us more torque. So what we see is torque and lever arm thumbs up, thumbs up. If you increase the lever arm, you increase the torque. And of course, increasing the torque means you have more success at possibly loosening the bolt. Case in point, I several years ago had a Honda minivan and the timing went out. That meant we had to replace the timing belt. And I went to Priority Honda at the time, and they were running a great deal. It was going to be $1,480 to replace the timing belt. And I was like, I'm a teacher. I can't, I can't afford that. So I said, screw it. I'll just fix it myself. Well, it turns out the timing belt cost me like $20. I think that was about it. And then I went ahead and bought a a water pump while I was doing it because I knew that was going to be a part as well. And I think that cost me another $10 or something like that. But the big problem came when I took everything apart like I was supposed to. You have to do some stuff to the engine and stuff like that, and then you got to reach the actual location where the timing apparatus is, and that's supposed to have been a pretty significant amount of torque applied to it. But it seemed that someone had actually put in thread lock in it because I couldn't loosen it with anything. I used a impact wrench that was putting out 1,200 foot-pounds of torque, and that didn't budge. I used a breaker bar. Basically, you can take a ratchet with a long handle, and then I put a bar on that to extend it like 8 feet long, and I still couldn't budge it. In fact, what happened was I ended up breaking my tools because I had some clutch tools as opposed to uh, Snap-on or Mac tools or something like that. If you have Snap-on or Mac tools, they're made of an entirely different type of steel. It works so much better. And in fact, I had to go borrow some tools. And then finally, what I did was I took the wrench, which now I'm using Mac tools and Snap-on tools, and I had a 4 foot extension coming from outside because I had to come out of the wheel well. And then I had a socket wrench that was basically about 2 feet long. Then I had a 4 foot long breaker bar that I stuck on the end of that, and I put all my weight on the end of that, and I still couldn't budge it. So the next thing I did was my friend told him about it. He happened to have the barrel off of a off of a gun. I think it was a F-16 or something. He was in the Navy, and he was a Navy chief in ordnance. So he happened to have the barrel of a gun, which was about 6, 7 feet long. And it just happened to fit right in the end of my breaker bar. So instead of having about a 6 foot long lever arm, I ended up having roughly a 12 foot long lever arm. And then I stood on it and finally it broke loose. So that's a good story about how the farther you are from the center of rotation of the nut, the more torque you can get on it, and therefore you can break it loose. So torque is directly proportional to lever arm. Now, the other thing is, if since we've already established that it would be better to pull up here instead of here, the other question is, would it be better to use a small force or a big force to try to loosen that? Anyone have any idea on that? Small force or big force? This thing working? Is my audio working? I just had a bunch of people that aren't not answering any questions today. So obviously, it take a big
A
force,
big
and
force.
therefore we say the torque is also proportional to the force. But not only that, we can, for instance, apply the force exactly perpendicular like that, but we could also apply the force at some crazy angle like this instead of 90 degrees. And when you take that into consideration, what you realize is really the only component of force that's going to matter is not the component of force that's parallel to the lever arm, but specifically the component of force that's perpendicular to the lever arm. So you could break this green vector up into this vector and then this vector like that. This particular component does nothing but tries to make the wrench fall off the nut, and we don't want that. This one, however, does do it. So, in fact, what we need is if we, and I shouldn't have used that particular angle, I should actually, let me use a different angle. Instead of saying it's down there, we could, for instance, say it is this angle. No, that angle is good. Yeah, I thought I'd drawn the right one, but it was looking funny when I went to do it, but now I see it's right. So yeah, we'll stick with that angle, and that angle right there is theta. And if you want to access this particular part, you see that I have to use the sine theta. So in fact, you get torque is equal to as proportional R times F times the sine of theta. And some of you might recognize this as the formula for the magnitude of the cross product, in which case you'd reach the conclusion that torque, the vector, is equal to R cross F, the vector, because the magnitude, if you write A cross B, the magnitude of A cross B is the magnitude of A times the magnitude of B times the sine of the angle between them when they're tail to tail. So it has to include this diagram. There's the A vector, there's the B vector, they're tail to tails, and that angle is theta. So with that, we now know a more general expression. I haven't necessarily taught you yet how to do the cross product, and I'll show you that in a second. But the main thing is we now have a reasonable explanation for what the equation for torque is. Now, it's actually a little bit more involved in that because there's a bunch of different ways you can calculate it and a bunch of ways that would give you the right answer and would take a lot less work depending on one diagram versus the other, or specifically what kind of problems you're solving. Sometimes problems have you use one version of the torque formula, and then another problem would be more easily done with another version. So let me show you all the various versions of the torque. So the magnitude of the torque could equal the component of R that's perpendicular to the force times the force. R, it could equal the component of force perpendicular to the lever arm times the lever arm. That's the R I keep talking about. R, you could use R times F times the sine of the angle between them. And then finally, you could use torque, the vector quantity, and this is another pseudo vector slash axial vector. This vector is the determinant of a matrix. Now, in order to do a cross product, this is actually how you do a cross product. You take the determinant, or how you can do it. There's a bunch of different ways, but in this case, we're going to take the determinant of a matrix, and that matrix is going to have its first row be I hat, J hat, and K hat. The second row should be the first vector, and what I said was torque is equal to R cross F, not F cross R. So the first vector in the cross product is R, so that means you need to put R sub X here, R sub Y here, and R sub Z here. And then the second vector, you put the components down here, F sub X, F sub Y, F sub Z. So all of these four ways are ways of calculating the torque. And this last one with the determinant of a matrix actually gives you a vector quantity. So it's kind of nice. And again, it's technically sort of an axial vector, but that's okay. We can use it. Now, how do we go about doing this? Well, what we normally teach, at least in the physics class, is the cofactor method. And you might have heard that Leibniz was one of the first people to use that, and therefore, in some sense, probably the discoverer of it. But what you can do is you can expand on a single entry in the determinant, or specifically in the matrix. And then you can use the next one and then the next one. So you need three of them to expand upon. And it's any three that you want. What we've discovered is really convenient is to expand upon first the I hat, then the J hat, then the K hat. When you go to do that, there's very specific rules about what you do. So the first thing you do is you write down exactly what it's going to be, because it turns out you can actually do the matrix, the determinant, another way. Let me show you really quickly, and hopefully that'll give you some idea of why I'm telling you this and why it works. So if we had I hat, J hat, K hat, R sub X, R sub Y, R sub Z, F sub X, F sub Y, F sub Z, like that, we could actually write that first column again. So just be F sub X. And then write that second column again, and you'll see why in a second. Because it turns out that the determinant is really a chance to multiply everything. In other words, we're literally talking about multiplying each number by every other number in the matrix. So to do that, what I'm going to do is imagine multiplying diagonally this way, and then diagonally this way, and then diagonally this way, and I'm going to add all those quantities. And then I have to try the other way, And this time I'm going to subtract all those quantities. So I'm going to multiply this way and say minus that result, and then this way and say minus that result, and then this way and say minus that result. So what do we get when I do it this way? Let me show you. It's really not that hard. It seems a lot worse than it is. What we're going to get is I hat times R, Y, F, Z plus J hat times R, Z, F, X plus K hat times R, X, F, Y. Now I've done the first three purples, which are the adding ones, and now I'm going to do the subtracting ones. I'm going to say minus K hat R Y F X minus I hat R Z F Y, and then minus J hat R X FZ. And of course, you can simplify that a bit by getting common terms together. So I'm going to say, let's take the I hats. That's going to be R, Y, F, Z minus R, Z, F, Y, I hat. That takes care of that one and that one. Now I'm going to take the J hat, and that's going to be RZFX minus RXFZ. J hat, that takes care of that one and that one. And now all I have left is the K hat. So I'm going to say plus. Now the positive K hat is RXFY minus RYFX, and that's times K hat. And that's actually the right answer. Okay. Now, to do it the way that your book is teaching you and the way that I'm really wanting to teach you, I wanted to show you that so you'd have some deeper understanding of what the determinant is. It really is a process in which you sort of multiply everything by everything else and then add them in some weird way. Uh, so you've seen how that worked out. Now, in this case, what we're going to use is these cofactors. So I'm going to expand on the I hat, and in so doing, there is a automatic factor of plus or minus one. So the way we incorporate that is we say equals -1. Now remember, I hat is in the first row in the first column. So we normally write the parts of a matrix, for instance, as the matrix M. The first row, first column would be M sub 1, 1, where the first one is the row number and the second one is the column number. So when you think about it that way, you can see that this one is 1, 1. This one is row 1, column 2. This one is row 1, column 3. This one is 2, 1, 2, 2, 2, 3. This one is 3, 1, 3, 2, 3, 3. So that's just the index notation that we use. The first number is the row number, the second is the column. So row by column is what we're talking about here. Now, with that in mind, since we're expanding on the I hat, I have to raise -1 to the I hat, or I plus j power, the index 1 plus 1. So that's equal to 2. And of course, -1 to the 2 power is just 1. But now I have to write the I hat out in front because that's the thing we're expanding upon. And then I have to realize that, all right, now that I have taken into account this one, I can't have anything from this row or this column, and that leaves just this matrix right here. And I just do the determinant of that 2 by 2 matrix by multiplying this times this minus this times this. So in this case, we're going to write it as RYFZ minus RZFY. So that's the first term with the cofactor. Now, the next thing we do is we have to use another cofactor. I'm going to J next. So next I'm going to write plus -1. Now, J has a 1 and a 2 as the indices, so that's 1 plus 2. That actually gives me a -1. And to do that, what I'm going to do is normally I don't actually write the -1 out there. What I do is I remember this means I'm cutting out that column and that row. So all I have left is these two guys and these two guys making the 2 by 2 matrix. But because 1 plus 2 is 3 and -1 to the 3 power is -1, I actually do the determinant backwards and that takes care of the -1. So I'll erase the -1 here. I just wanted you to know where it came from. Now I'm going to write down j hat, and now I'm going to take the matrix, the determinant of the remaining 2 by 2 matrix backwards. So instead of going uh, this minus this, I'm going to go this minus this. So I'm going to do RZFX RZFX minus RXFZ. And that's my J hat. And then plus, again, you'd put a -1, but it'd be raised to the 1 plus 3 power. That's the 4 power. So I don't have to do that, but I'll write it right here just the same. And then I'm saying times K hat. And now, since I've used K hat, that means this column and this row are out. So that leaves this 2 by 2 matrix. And I'm going to say that minus that, which is a normal determinant. So I'm now going to say RXFY, RXFY minus RY X, like that. And of course, this tells us that the cross product is in fact RYFX minus RXFY I hat plus RZFX minus RXFZ J hat plus RXFY minus RYFX K hat, which I think you can see is exactly identical to the version I got below. So I've now shown you basically, in practice, probably three different ways of calculating a cross product. You can just blindly apply this formula right here because that's actually going to be on your equation sheet. It's been on your equation sheet all this time. So you can actually apply this equation for any cross product, but you can also use this matrix and minors method that I used here. But as long as you're doing 3 by 3, there's problems if you go to higher order dimensions. But in the 3 by 3, you can always do it this way as well, and that works too. So those are a bunch of different ways of calculating torque. Now that we've had that, you now have a pretty good understanding of how to compute torque. And as I said, it's either the component of the lever arm that's perpendicular to the force multiplied by the force, or it's the component of the force perpendicular to the lever arm multiplied by the lever arm, or it's the magnitude of the lever arm times the magnitude of the force times the sine of the angle between them when they're tail to tail. That's three of the ways to calculate the magnitude. And then, of course, you can use the right-hand rule. The right-hand rule, by the way, for cross products is you hold your fingers like this, and in all honesty, the middle finger doesn't technically have to be at 90 degrees. The only thing is, if it's at 0 degrees from the index finger, then the cross product will be 0. Or if it's 180 degrees from the index finger, then the cross product will be 0 as well. So you normally hold your hand like this, and what it's saying is this is the first vector in the cross product is your index finger. The second vector in the cross product is your middle finger, which, like I said, can be anything but 0 or 180, and you can move it all those different ways. And then mutually perpendicular to both of those directions is the thumb, and that's the direction, again, using your right hand, that's the direction of the cross product. So in fact, when you take a cross product of A and B, you get a vector that's perpendicular to both A vector and the B vector. So if you had the magnitude in the right-hand rule, that's just as good as doing the cross product with the matrix and everything. It's just sometimes in 3D, it's really hard to do all that by eyeing it. So you really need some brute force methods like this matrix here. So Now let's go ahead on and work an example. So example 10.7 is a pretty straightforward one. I'm going to go ahead and switch back to blue. I'm going to cross this line out here. And we're going to say example 10.7, bicep torque. The biceps muscle exerts a vertical force on the lower arm bent as shown in figure 10.15a and b. For each case, calculate the torque about the axis of rotation through the elbow joint, assuming the muscle is attached 5 centimeters from the elbow as shown. So in the first case, you can see that we basically have the force being perpendicular to the actual lever arm, if you will. It sort of doesn't look like it. Well, I can't really draw it, but let me share the screen real quick and show you what I'm talking about here. Nah, I don't want to do that either. Okay, well, let me show you this way. So what we're imagining here is that your forearm is like this, and then there's an elbow joint right here, and then there's an arm like that, and then this is your hand. Something like that. And your bicep muscle is like this, and it attaches right there about 5 centimeters. And in fact, it applies a force upward, and that force is 700 newtons. Okay. Now, what you see is there's a lever arm vector, and it's not as easy to see in the diagram that the book gave you, but in my diagram it is, and that's why I decided to go ahead and draw it. But that's the lever arm vector, that little R right there. And you can see that the R is in fact perpendicular to F. So this is part A, by the way. So for A, we've got torque is equal to R times F times sine of theta. R, it's R perpendicular times F. R, it's F perpendicular times R, so on and so forth. Either way, I'm going to say the R is 0.050 meters times the force is 700 newtons times the sine of the angle between them. Now remember, the angle between them is when they're tail to tail. So if I made it properly, oops, if I drew the diagram properly, we would show R like this, and we'd show F like this. So now you see they are in fact tail to tail, and you see the angle between them, theta, is equal to 90 degrees. So we can go ahead and write times the sine of 90 degrees. And of course, the sine of 90 is just 1, so I get 0.05 times 700 times sine of 90 degrees. Oops. And I see now that my calculator had some random button pushes on there. That was not helpful. 0.05 times 700 times sine. Okay, so this gives me 35.0, and the units for torque are the Newton meter, which you might remember is the same thing as we found for the energy, which is a Newton times a meter, but we keep it as a Newton meter when we're talking about torque. We don't call it a joule. So that is the torque for part A. And of course, that's just the magnitude. But if you wanted to actually calculate the vector, it's R cross F. So we put our index finger pointing to the right, we put our middle finger pointing up in the direction of the force, and then the thumb is pointing out at me. So the torque is toward me. Now for part B, it's a little different, and it even gets a little worse. It makes it kind of more difficult to really see because they're doing something abstract with it, which is an actual arm. So it makes it a little bit of a problem. But in that case, let's see if I can draw something somewhat reasonable for you. So we're still going to have the upper arm straight up. We're still going to have the elbow like this. And in fact, what we're imagining now is the lower arm. That lower arm is now at a 30-degree angle. So in this case, you can say that the force, of course, is still vertical. But now the lever arm is actually tilted a little bit. And the way your book has it drawn, it's like the force doesn't go any lower, even though the arm's lower. So that makes it a little bit more confusing. Uh, but what we can see is, in this case, we can say the lever arm vector is something like that. It's still 5 centimeters away, but you can see that with the purple vector pointing this way, oops, supposed to be a purple vector there. The purple vector pointing this way, and we want them head to tail. So the R vector is pointing this way. You can see that this angle is actually 90 plus 30 degrees. That's not necessarily very helpful, but that's what it's supposed to be. And we know for part B that the torque is equal to R times F times the sine of the angle between them. But we also know that sine looks like this. So this right here is this is 180, this is 90, this is 270, and this is 360 degrees. And what we're looking at here is 120 degrees, which is 30 past 90. So if I go 30 past 90, that's 120 degrees. But that should be the same thing as 30 less than 90. So this is 60 degrees. So we can go ahead and say that in this case, torque is equal to 0.050 meters times 700 newtons times the sine specifically of 60 degrees. We could use a sine of 120, that would work as well, but I was just showing you because your book ended up using 60. I wanted to show you that the reason why you can use 60 is 60 and 120 are the same angles, at least from a standpoint of a sine output. So now I say 0.05 times 700 times sine of 60, and that gives me 30.31. Newton meters is equal to torque for part A. I mean, for part B. Anybody have any questions on that? All right, so you didn't necessarily have to do all that thing where I figured out the fact that it was 30 degrees beyond 90, but I wanted you to understand why your book is using theta equals 60 degrees, and why it's equivalent to it. I generally think of the vectors as if they're being tail to tail, and then sometimes you have to do some stuff like that to make it make sense to align with other people's interpretation. But there are other ways, and there are trig identities that can help you do it and that sort of thing. Anybody have any questions on that one? All right, let's jump to example 10.8 where we're actually going to do another calculation of torque. So example 10.8, and this one says torque on a compound wheel. Two thin disc-shaped wheels of radii RA equals 30 centimeters and RB equals 50 centimeters are attached to each other on an axle that passes through the center of each, as shown in figure 1017. Calculate the net torque on this compound wheel due to the two forces shown, each of magnitude 50 newtons. So what we have is RA is equal to 30 centimeters. RB is equal to 50 centimeters. Notice I put the 0 with a bar under it so we could at least sure up the fact that these both have two sig figs, and they're attached to an axle. It passes through the center. Of course, the two forces are FA equals FB equals specifically 50.0 newtons, like that. And now I'm going to draw a picture of the wheels so you can have some sense of what we're talking about here. I'm going to try to draw these centered up as best I can and circular. So let's draw this circle first. And now I'm going to draw this other circle. And I'm going to try to hit all these marks like this. So this circle, like that. So that looks pretty good. Not as good as I would like, but it's good enough, I guess. And they're supposed to be two basically concentric circles. I think I've got it pretty close to that now. So one has an inner circle, and what we're talking about here is a force of 50 newtons pointing down. And the other one is acting on the bigger part. And if you imagine this is tangential at that point, then this force is 50.0 newtons at 30 degrees, which you could also interpret that this is 60 degrees. Either of those would work. And more specifically, we need to know that this distance is RB and that this distance is RA. Okay. So we can draw the lever arm in both cases. The lever arm is the vector from the center of rotation to the point of application of the force. So that's the R sub A lever arm. And this one is the R sub B. Or excuse me, this is the R sub A, and this one's the R sub B. Okay. The main thing is, and this is why they drew that 60 degrees in there, you can see that if you slide the RB vector up in my diagram, then it will become tail to tail with that force, and you'll see that the force between the, or the angle between them two when they're tail to tail is 60 degrees. So we can calculate the torques as follows. Let's first off say torque sub B is equal to R sub B times F sub B times the times the sine of the angle theta sub B. So that's going to be R sub B is 50, so 0.500 meters times 50.0 newtons times the sine of 60 degrees. And by the way, if I wanted to say which way this is rotating, I would have to spin my hand like this and have my fingers curl around this way, because the torque for this particular R sub B and F sub B is tending to rotate it in a clockwise direction. That means this one should point into the page. So the right hand rule tells us this torque sub B, is into the page. And I'll compute it and I'll write that as its direction as well. So 0.5 times 50 times the sine of 60 gives me 25 root 3 over 2, which is 21.65 Newton meters into the page. Okay, so that is our torque sub B. And I'm going to go ahead and box it off just so we'll have it. Even though that's not the final answer, I'm just boxing it off so it'll be easy to find. Now we're going to say torque sub A, and that's R sub A times F sub A times the sine of the angle between them, theta sub A. But you can see in this case, the angle between them is clearly a 90-degree angle. So sine of 90 is just 1, and that makes life a lot easier. So in this case, I'm going to write 0.300 meters times 50.0 newtons times the sine of 90 degrees. And in this case, it's 0.3 times 50, which gives me 15. So I'm going to say 15.00 Newton meters. And this one, of course, is out of the page. And that's torque sub A, and I will box it off as well. But what they asked us for specifically was calculate the net torque. And the fact that they're pointing in two different directions just tells you, hey, 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 one of these should be positive, one of these should be negative, and it doesn't matter which, but the main thing is, they're fighting each other, so they have to subtract. So torque net is going to be 21.65 Newton meters minus 15.00 Newton meters, which gives me 6.65. And technically, it's only one sig fig, so that's why I often don't like using two sig figs, because the answers often come out to be less than two sig figs. But that's the total torque. And of course, since the 21.65 was bigger, that was the one we called positive, and that means the net torque is pointing into the page. So I'm going to do this and say into the page, and that implies counterclockwise rotation. Okay. Any questions on that one? All right, and your book got negative 6.7. That's pretty normal. Generally speaking, counterclockwise rotations, I generally call them positive. In fact, one of the things that I often use, and I've mentioned this before, is when I'm solving a problem that's at least two-dimensional and I have a lot of vectors, Newton's second law and stuff like that, I'll write something like this, and I've mentioned this to you before, and I just put a plus in it. And what that means is positive x is to the right, positive y is up, and counterclockwise torque is positive. With that being the case, since the counterclockwise torque is positive with my previous diagram, I'd actually call that a negative torque as well, which is the same thing your book had. Your book said negative 6.7, so that's about right. But that's some terminology and some symbology that you can use when you're, for instance, working in your statics class or something like that. Anybody have any questions on that? All right, now here's the big deal, rotational dynamics. This is where we start to actually apply the dynamics as opposed to the kinematics. And I'm going to draw a nice, crisp, well-drawn red line to separate this. And now we're going to get into Newton's second law. So there's a couple different ways we can write Newton's second law. We can say the summation, and I'm going to put this with Newton's second law the regular way. So the summation of the forces is equal to mass times acceleration. That was one version of Newton's second law. And the rotational analog is the summation of the torques is equal to I times alpha. So that's equivalent. We also learned another way, which is the summation of the forces is equal to dP dt. And of course, the rotational analog for that one is the summation of the torques is equal to dL dt. And I should point out that I is equal to the summation m sub I r sub I squared. R, it's equal to the integral of r squared dm. And I should point out that L is equal to r cross p, but also that L is equal to I omega. So that's a couple different ways we could write these as well. But those are actually the equations that we're going to use. And the big thing is you really have to have this with a fixed axis. It specifically says axis fixed in an inertial reference frame for the summation of the torques equals I times alpha. And if you want to write it as a summation of torques about the center of mass, let's go ahead and write it the way they have. So I'm going to write the summation of the torques is equal to I times alpha. And this one says axis fixed fixed in inertial reference frame. Okay, meaning you have to have a reference frame that's inertial, and then the axis is sitting perfectly still in that. And inertial reference frame means any frame in which Newton's first law or Galileo's law of inertia appears to hold. But then there's another one where you don't have to use an inertial reference frame. You have another version of the equation, which I'll write this one in red to show you that it's different. But the summation of the torques about the center of mass, that's the key thing here, is equal to I about the center of mass times alpha about the center of mass. And this one is for an axis fixed in direction. So the axis has to be fixed in direction, but may accelerate. So, for instance, if you're considering a ball rolling down an incline, if the ball's not wiggling and stuff like that, then the ball will roll straight down the incline. The axis stays in a fixed direction. It's always pointing straight ahead of me because it's rolling down this way. So the axis is pointing that way. And even though that thing is speeding up, speeding up, speeding up, it's a non-inertial reference frame. It's actually speeding up. As long as we take the torques about the center of mass, then I'm perfectly fine with using summation of the torques equals I times alpha. And that's what they're trying to show you here in this section on rotational dynamics, torque, and rotational inertia. So now that we have that, we can actually start solving some physics problems about it. So let me start with example 10.9. We still got about 23 minutes left, so that's why I'm pressing on. So example 10.9. And this one says two weights on a bar, different axis, different I. So two small weights of mass 5 kilograms and 7 kilograms are mounted 4 meters apart on a light rod whose mass can be ignored. As shown in figure 10.20. Calculate the moment of inertia. Oh, have y'all been able to hear me at all? God, this is terrible. I just realized all this time I wasn't wearing that. Are y'all there? Thank you. Have you have been able to hear me, Mihak? I am so sorry. I just realized all this time I haven't even been wearing this. I might have to re-record all this. Oh, this is awful. Anyways,
Yeah, I was
you
able to hear you.
oh, good. Thank you. Whew. Okay, that really scared me. Sorry about that, everybody. Now I know one was answering me. Y'all probably were answering me all this time. I'm looking like an idiot. Jesus. Anyways, okay. So it says calculate the moment of inertia of the system A when rotated about an axis halfway between the weights, and B when rotated about an axis zero point 0.5 meters to the left of the 5 kilogram mass. So let me start by saying drawing a diagram. I think that's the most fruitful way here. So here's my x-axis, and here's my y-axis, which I'm going to treat as if it's the rotational axis as well. And what I have is two small weights, 5 kilograms and 7 kilograms, are mounted 4 meters apart on a light rod whose mass can be ignored. Calculate the moment of inertia of the system A when rotated about an axis halfway between the weights. So what we're picturing here is this side is 2.0 meters. And in fact, we have a mass of 7.0 kilograms. And then on the other side, we have a mass of 5 kilograms, but it too is at 2.0 meters. And in this case, it's 5.0 kilograms. And I'm going to show the rotation like that. So we're saying that's what's going on. And what we're supposed to do in part A, which is this figure here. So for part A, what they want us to calculate is the moment of inertia. So I with axis centered equals question mark. And then for part B, we're going to say, okay, now I have the 5 kilogram mass, and this distance right here is 0.50 meters. And then 4 meters away from that, 1, 2, 3, 4, roughly here, is the 7.0 kilograms. And this distance, of course, 4.0 meters, is like that. Okay, and this is part B. And for part B, we want to know I equals question mark. So first off, let's take A. I equals the summation from I equals 1 to n of m sub I r sub I squared, where r sub I is supposed to be the distance measured perpendicular to the rotation axis from the rotation axis to the actual mass. And m, of course, is the mass. So in this case, we're going to write that we actually have the 5 kilogram mass 2 meters away, so it's 5.0 kilograms times 2.0 meters squared, plus we have the 7.0 kilogram mass, and that too is 2.0 meters away, and I'm going to square that. Obviously, this becomes 5 times 4, which is 20, and 7 times 4, which is 28, so this is going to be 48.0 kilograms meters squared, and that is the units for I. So I'll write this as I center. So that's part A. And that should make sense to everyone. Notice the units are kilograms, meters squared, and actually that gram looks really horrible, so let me fix that just a little better. Now let's do part B. I is going to be, now the axis of rotation, I didn't actually draw it on here, but there it is. It's actually rotating to the left of the 5 kilograms.
So in this case, I'm going to say 5.0 kilograms times 0.50 meters squared plus 7.0 kilograms. And notice this one's 4.50 meters away. And we're going to square that. And that's a little bit bigger. So I'm going to do a calculation on this with my calculator. So 5 times zero point 0.5 squared plus 7 times 4.5 squared gives me 143 kilograms meters squared equals I about the end, something like that. Or I'll say N plus. So that's the moment of inertia for those two different configurations of the same thing. Anybody have any questions on that? All right. Well, we've got a little bit more time left, so I'm going to go ahead and show you a calculation of the moment of inertia using the integral. So let's go ahead and, for instance, I'm going to consider this example is just one I'm making up. So Mr. Y's example. Oop. So in this case, I'm going to say, here's my coordinate system. And what I'm going to do is imagine I have a rod, a uniform rod of length L and mass M. Calculate, oh, darn it, there it goes again. Calculate the moment of inertia, which I'm calling I, of a uniform thin rod of length L. Actually, I want to make that a capital L. Length L, mass M, if it is rotated about an axis through its center. That's going to be part A. Part B, what if rotated about left end? Okay. So, given our description, I'm going to say this end is at L over 2 and this end is at negative L over 2. And I'm going to proceed as follows for part A. I equals the integral of r squared dm. And of course, we always use our dm in the way we told you. And in this case, I'm going to imagine right here that this width right here is dx. And this quantity is dm, which equals lambda dx. Now, for the record, lambda would have to be equal to m over L. Oops, I wrote lambda, said lambda, but I wrote L. So, sorry, lambda should be m over L because it's uniform. Okay. And you can say the perpendicular distance, perpendicular to the axis, that perpendicular distance to that piece of mass is r, which is really just our x variable. Okay. So with that in mind, I'm going to say the integral from negative L over 2 to L over 2 of x squared lambda dx is equal to 1/3 lambda x cubed from negative L over 2 to L over 2, which is going to be 1/3. Now, lambda I said was m over L, so I'm going to go ahead and put that in. And then now I've got to do L over 2. That's going to be to the third power minus negative L over 2 raised to the third power. And that's going to give us 1/3 m over L times, now it's going to be L cubed over 8 plus L cubed over 8. Notice the negative cubed gives you a negative, and then L cubed over 8 plus L cubed over 8 is L cubed over 4. It's 2/8, and 2/8 is 1/4. So that's going to be 1/12 ml squared is equal to the moment of inertia. So that's the answer, 1/12 ml squared. And if you actually looked at uh, the table on uh, the previous page or in section 10.6 or 10.5, it's page 276. If you see that, that's exactly the formula you get. So now I'm going to do the same thing for part B because we've got 10 minutes left. So for part B, in this case, I'm going to say I is equal to the integral r squared dm, which in this case is going to be the integral from 0 to L of x squared lambda dx. So we're doing the same sort of process, only now I've moved the axis of rotation to here for part B and to here for part A. So now that distance from the axis is still just the just the variable x. And since I've shifted it all, it now goes from 0 to L instead of from negative L over 2 to positive L over 2. But it's pretty straightforward from here, you can see. We're going to get the integral of x squared is 1/3, so that's going to be 1/3 x cubed. And that lambda is going to be m over L again. And then it's going to be x cubed, and in that case, it's x cubed from 0 to L. So we get 1/3, oops, 1/3 m over L times L cubed, which equals 1/3 m L squared, and that's I about the end. Now, there happens to be something called the parallel axis theorem. And the parallel axis theorem says that the moment of inertia about a parallel axis is equal to the moment of inertia about the center of mass plus m times d squared, where d is the distance between the center of mass and the new rotation axis. So I'm just going to use that formula real quick and see if we get the same thing. The ICM we already did is 1/12. So I'm now going to say I parallel axis is equal to 1/12 ml squared plus m, that's the mass. Now I need to multiply the distance between the old axis, which is dead center, and the new axis, which is L over 2 away. So I'm going to put L over 2 as the d, and of course that d has to be squared. So with this, you get 1/12 ml squared plus 1/4 ml squared. 1/4 is the same thing as 3/12. 3/12 plus 1/12 is 4/12. So you get 4/12 ml squared, which is equal to 1/3 ml squared, which is exactly the same thing we got before. So you can see the parallel axis theorem worked. The parallel axis theorem is something that you're responsible for knowing, and your book does explain it. The perpendicular axis theorem I am not covering, so you can skip that. Your book talks about that as well. It's a much more complicated formula to apply, so I'm not doing that. But I did do the parallel axis theorem, and you can see that you got exactly the same answer. When we meet next time, I'll do another one of these that's a little more taxing to do the calculus on. I'll do a rotating cylinder, for instance, and I might even come back and do this one with a non-uniform mass distribution. Like I could say the mass lambda, mass per unit length is equal to, 4x squared or something like that. And then because of that, it's actually getting heavier and heavier the farther away from the left end you get, or the farther away from the center you get, and that would make a much bigger moment of inertia. So I'll show you that next time, but this is enough for right now. Uh, you guys are free to go. We've got about technically 5 or 6 minutes left, but I'm going to wait here till the last person leaves in case anybody has any questions. Don't forget, we have an exam, a face-to-face test next week. You guys will be doing this in your lab, and it's actually going to be a sit-down paper test that I'm going to give Mr. Dr. Johnson the information for. So y'all will have that, and it's due, of course, that Wednesday day. The practice test has been up for some time, and it's still up, and it will disappear that day. And there's an online test due that morning by like 10 a.m. or something like that. So you want to make sure you do that as part of your prepping. So make sure you don't miss your online test. Make sure you don't miss your face-to-face test. But that all happens on Wednesday, by Wednesday of next week. So have a good one, everybody. Again, I'm waiting here for the last person to leave. Stay safe, have fun, and send me a text or whatever if you need anything. Thank you. Sorry for doing a whole half without my speakers on, without my headphones on. I was like, man, I feel so good. I feel free. You have any questions, Mihak?
No, not really. But I did have one thing.
Yes,
So
ma'am.
I didn't do too well on test two, but I did pretty good on test one.
Right.
So I'm just wondering, I guess the best way to study for this test. So I did the practice test quite a few times for the last one,
Mm-hmm.
but I guess it didn't seem to click as well based
Didn't
on my
click as well.
result.
Right.
Yeah. So just kind of wondering if you had any tips for this one so I could be, I guess like more successful.
If you were actually taking the practice test and you took it several times, that's pretty much
Yeah.
the best thing you can do. I would say the more you do it, the better off you'll be. Remember, we do have some integration problems that have to be done. For instance, like the problem on the actual face-to-face test that we did, where I gave you that acceleration as a function of time, and I
Yeah.
had an x component and a y component. Make sure you hit some of those questions, and also pay close attention to how your book does them versus how you're doing them. So a lot of times your book will start off with F equals ma, and then set
Mhm.
up all the equations and then solve. A lot of people were just jumping right into mg equals mv squared over r, that sort of thing. If you're doing that, you're missing some of the nuances of the different problems that you solve. So you might actually be mostly getting the answers right, but if you did enough of them, you'd find that you get quite a few of them wrong because they don't always apply that way. But by all means, if you run into any problems in the practice test or in the homework
Mhm.
that bother you, make sure you take a picture of it and send it to me and let me help you. It might be something where I can just send you a text message back and explain what you're doing wrong. It might be something where I need to set up a Zoom meeting for you so that we can talk about it. Whatever is necessary, we can do that.
Yeah, I think the thing that tripped me up the most was kind of like the like kind of visualizing like the incline forces.
Hmm.
I think that was what I was having the most trouble on. So what I've been doing is kind of like reviewing the lectures again and trying to
Yeah.
get a better understanding. Yeah.
Yeah, making those two separate free body diagrams, like on the Atwood machine
Yep.
on an incline, and then writing out F equals ma for the two dimensions on the incline, and then for the one dimension on the hanging mass. That's sort of the meat and potatoes. You got to do that step on just about every problem, and that was what a lot of students that didn't do so well did. Is they just sort of jumped in and thought they could just work out the answer based on looking at the figure. But if you don't take the time to write F equals ma for the vertical, tilted
Mhm.
y-axis as well as for the tilted horizontal axis, and then again for the other mass, then yeah, you're liable to make some mistakes. So yeah, it sounds like you're self-correcting pretty well. But like I said, if
Yep.
you don't get right answers, make sure you let me know. I am working on. Hopefully the pictures won't be so bad, but it looks like I've got to remake my whole test bank kit. So that's what I'm going to spend the
Yep.
whole weekend doing. Yay for me!
And I guess last thing, I know test two wasn't as test one heavy, so would you say like the next test is gonna be like focus, I guess, more on the new stuff and not as much on chapter two? I just want to make sure.
Yeah, because when I saw test one and I saw test two, my class averages were pretty good. Usually, when my class averages aren't that good, I look back at test one and say, "Well, what did people miss?" And then I make sure that's on test two, and then I do
Got
the
it.
same thing with test three about test two. But my class averages were good on one and two, so instinctively, I would say it's more about the latest material. But all of my tests are fundamentally comprehensive because that's just the way physics works.
Yeah.
So,
All
but
right.
yeah, I would think it
Appreciate
would
it.
be pretty much the most recent stuff would be more critical than the old stuff.
Got it. So more of the new chapters. Alrighty.
Yep,
Yeah, I'll try working on kind of fixing the stuff from last test and just getting a better idea on the incline stuff. And if I have any questions, I will definitely reach out to you and I'll start working on the new stuff as well. Make sure you get that.
that's good. Am I pronouncing your first name right? Is it Mihak or is there a better way of
Yeah,
pronouncing that?
Mahak.
Okay, Mahak. Gotcha. I'm
Mhm.
making it sort of the first syllables the most pronounced one, and that's not necessarily the case. That's cool. Well, thanks, Mihak. I appreciate you coming. And
Yeah,
do
of course. Have a
contact
good.
me by text is the most efficient way if you have any problems. But of course, you can email me too.
Sounds good. All
All
right.
right.
Thanks so much. See you next class.
Thank you. See you then. Bye bye.
Bye.
All right. So that's it. Have a good one, everybody. Bye bye.